Welcome to this very last APL Quest video. See APL Wiki for details. Today's quest is to split a text on spaces, and there's a specification left argument which tells us how many segments to cut into. And basically, we want to be greedy and split at leading at the first coming spaces until we have as many segments as required. And if the number of segments required is larger than what we get just by splitting on spaces, then we need to add empty segments at the end. So let's get started. Here is a sample text. And let's first try this as a tacit function. Now, there's a couple of classic ways to split on spaces, and this is one of them. So what we can do is we can start off with the argument and concatenate another space in front. We can kind of make out the space over here. The reason we need this additional space is so that we can compare with the space, and that gives us this mask that we can then use to partition the right argument. And this gives us a cutoff set here. But we're a bit off. And that's because we added a space at the beginning so that we would include the leading text. So instead of splitting the original, we can split the concatenation. Okay, that looks more sensible to work with. Here's a trick though. Since we want to potentially add empty segments at the end, we want this nested array to have a prototypical element which is such an empty character vector. And we can do that by injecting an empty one at the beginning. We could do this manually, but we can actually do this kind of what I would call automatically. And how can we do that? Well, if we go back and to how we created this mask, then we can say we concatenated a space in front so that we would get a 1. But we can also add a 2 manually, or for that sake, a 1. But by adding a 1, that tells partition function that we want 2 segments to begin here, so we get an empty one at the beginning. And now we can use this to partition the concatenation of that space with the original argument. This has the benefit then that if we take too many elements, say 6 elements here, then we pad with empty elements at the end. If we didn't do this, and we try to take too many elements, say 6 here, it would actually be 5 to be similar, then we pad with elements that are not empty because they're based on how long the first element is. So this solves that problem. And now, really, all that remains is to take this and merge as many trailing elements as required so that we have the right number. And then finally, we need to remove this leading element that wasn't there. And possibly, we're going to take more elements than there are, and they will be padded automatically. So now, let's add the left argument. Let's do 3 for now. And so we can take the left argument and take from here. That gives us the leading elements that we're supposed to preserve. And then we can use a drop, and that gives us the trailing elements that we want joined together. So we can combine this by saying we take the leading ones followed by the trailing ones. This is, of course, the whole thing. But before we do this concatenation, we're going to post-process the drop with joining them together. That's a concatenation reduction. So we insert concatenation between all these elements. So we do that on top of the result of the drop. So now we've joined the last, and we get a total of 3, except, of course, the leading one that we inserted just temporarily to get the right prototype. This means that we can strip the leading one, and we can drop the leading element from each one because we had that one space here that we don't want included now that we have split on spaces. So this works for 3, and for 4 you get the exact fit, and for 5 we have the take, add and additional elements, and so too for any higher number. So this is one solution to the problem. Here's another solution to the problem. We can start off the same way by concatenating a space on the left. And let's call that S for added a space. And then we can make our mask. Before we did that with a tacit subfunction, but now we can do that explicitly like this. The pass-through value of an assignment is the value that's on the right of the assignment arrow. So we can use that directly. The first element of S is going to be the space. Then we don't have to repeat ourselves. This gives us our mask. And now we want to change this mask. Essentially, we want to get rid of ones that are over here if we don't want a new segment to start there. So rather than creating all these segments and joining them together, we don't want to create them from the outset. How can we do that? Let's run an addition scan. That gives us the running count of ones here. And then we have a left argument, which is the maximum number of segments that we want. So if we clamp here, then all these 4s become 3s. But we actually wanted a mask. How can we get back to a mask? Well, all these numbers are necessarily unique since we are always increasing or staying the same. That means that the ones correspond to the first time that any one of these elements occur. So there's a 1 at the beginning of the 1s, there's a 1 at the beginning of the 2s, and there's a 1 at the beginning of the 3s. And we can do that using the unique mask. Unique mask indicates the first time a unique element appears. So now we're back to the mask, but the one that indicated where the 4s were supposed to begin is gone. If we put in a 4, then we preserve all of that. And if we put in a 5, then nothing more happens. We're not clamping anything. Okay. With this, we're almost ready to partition. The problem is that if we take this text and we try to partition it, it all works nicely for this case. Oh, actually, we shouldn't be using the original argument. We should be using the one that has an S at the beginning so that we stay consistent. But if we have too many segments that we want, then we don't get enough. We want empty segments at the end. And we can do that by telling partition enclose that we want trailing elements. We do that by adding a number at the very end of the mask that's the one element beyond the corresponding to the last element of the data, which is the count. Now we could compute how many are necessary to add, but they're all just the same empty elements and it doesn't really matter. The maximum it could possibly be is the number of segments that we want at all. This is of course too many, so we can strip down the ones that we don't want, simply taking as many as we do want. And now all that remains is to drop the leading space on each one. Thank you for watching.